All right, so for our final keynote at MuniHac 2024, we are very pleased to have Niki Vazou. Niki is a research professor at IMDIA in Madrid, and she's one of the authors of refinement types for Haskell and the tool Liquid Haskell. This paper actually was first presented 10 years ago, and at the last ICFP, it received the Test of Time Award. The award was given because the paper industrialized the verification technology of refinement types and presented Liquid Haskell, which is actively used 10 years later for education and for software verification. And yeah, are very pleased to have you here and talk about this very topic, refinement types.
Thank you very much. Okay, so thank you very much. Thank you for having me. I'm going to talk about refinement types and Liquid Haskell, which is the refinement type checker in Haskell. So, okay, let me start with a brief explanation what is refinement types. And the idea is very simply refinement types basically refine existing types with logical predicates. And as a standard example, we have the indexing function in Haskell. So this indexing function takes as input a list of A's, an index, and returns an element of the list, right? And of course, like this is a very dangerous function because the index can get out of bounds. And like by default, this inbound indexing is a specification that we cannot use, we cannot give using Haskell's type system. So what refinement types do is they are refining existing types with logical predicates to express this kind of specification that cannot be expressed in the current type system. So what we do with refinement types in Haskell is we say, I'm going to name the input list X's, and then I'm going to refine the index that I am using for this list and say that this index I is between 0 and the length of the input list, right? So I am using logic to refine the existing type to express safe indexing. And then we have Liquid Haskell, which is a refinement type checker for Haskell. And I have a video, but I can do a demo. So Liquid Haskell is a plugin for GHC. So you use your Cabal file. So thanks to Andres, Liquid Haskell ran as a plugin. So you just go into your Cabal file and you say, use the GHC plugin, right? And so now, when I am using Liquid Haskell and I am like as a plugin and I'm using the indexing operator, this has the inbound indexing requirement built in, right? Yes, and as of Friday, the Haskell language server works for my VS Code and for my Liquid Haskell. Okay, so now if I am just indexing I get, it works, right? Yes, nice. I get a liquid type error that says, look, like the index that you gave me is I, but I expect an index that is greater than or equal to 0. Okay, and so how do we fix that? We can add a runtime check and we can say if the index is indeed this, I can say then just do safe indexing, else nothing, and I am going to return a maybe. Okay, and we see that still I have an error, but the error is now different, and it says like Liquid Haskell takes the information that you have from the branching, right? It knows now that the index is greater than or equal to 0, but it says, okay, it has to be, like how do I do? It has to be below the length of my input list. So I can come and extend the check and say, okay, it also has to be below the length of X's. And now your program passes, right? Okay, the program is good. And so indexing is one of the operators that comes by default refined. And what is the other operator that like we don't, like what is another common operator that we need to refine? Yes. Hi, head, too. Okay, I can do head. Okay. So we say head. Plum, plum. No, that's not no. Because I have to do it head here, right? Okay. I'm going to have a list of leaves. I am scared now. But it doesn't. No. I do the wrong check. What does this mean? I have two, right? So you want me to do this? Head. And now I can remove this. Oh, head was not what I had in mind. Type I think I broke something different though. In the use of head, this is a partial. No, because GHC now complains for the head, right? Yeah, non-empty. So I guess I cannot go through GHC. Okay, let me revert. Like let me check this after. And okay, other than head, the standard operator. Yeah, okay, I'll check this after because I don't know what happened with GH error. But it shouldn't be an error. It should be a warning. It's a warning, so I don't know why it doesn't go through there. Okay, other than head, we can check it after, which also has a precondition that says like it has to be different than 0. But the other operation is division, right? So I can say divide what you get by this and this. Okay, I don't know why here didn't work. Okay, after the talk I'll check. Okay, yes, I am dividing with something that I called from, I took like with the ith element of the list, and I get an error that says like you got some element A, and this has to be different than 0, and I cannot prove this thing. Okay, so now to prove this thing, I could also like inject a runtime check and everything, but like refinement types have this property of giving specification using collections of types. So like as an input, we have a list of integers, and what I can do is I can go and give a refinement type using these special comments, and okay, it still says like I don't know anything about what I got from the list, but I can say that all the elements inside my list are values v, and these values are different than 0. And now it knows that everything I get from the list satisfies this predicate, so it's a good operation for the division, right? Okay, so we used like we used the special comments, and we said we gave a specification for test. So now we can make it one step further and try to remove this runtime check by just pushing it into the specifications of the refinement type specification for test. So I can say my input list, I name it x's, and the index is an I, and this I should be between 0, I, and I is less than the length of x's. And now that I gave the specification, I can go and remove my runtime check, and hopefully Liquid Haskell is going to be happy. So we have a specification here, and we pushed it into the refinement type of the user function. And now if I am going to call test, so I say bar test 1, 2, 3, 1, this is fine. And of course, like if I put 0 here, I have to take, yes, I take like that this list that you constructed doesn't satisfy the specification of test. And if I, again, like do out-of-bound indexing, it's again going to complain. So what refinement types are doing is basically they are taking the specifications of built-in functions and they are like pushing them up like to one runtime check at the beginning. Okay, and this is like the standard use of refinement types. I think Liquid Haskell is very mature for this kind of things. Like if you're dealing about nonlinear arithmetic for indexing or like division by zero or these like light properties, it's very good and it's like quite easy to use. And it can figure out many interesting bugs in your program. But there is a different use of Liquid Haskell that I really like and I mostly work on. I call it deep verification. And the idea is here, how can we use refinement types and Haskell itself to prove theorems? And here I have a theorem, right identity of append. And basically, it says that for all list x's, I want to prove using a refinement of, like I have unit, I refine it, it looks like a theorem. And the idea is here, how do I want to prove that if I append x's to an empty list, I get back x's, the right identity of append. And undefined like Haskell and Liquid Haskell, all types are inhabited by undefined. So that's a good proof, there is no complaints. But I want to do, it's QED, right? All theorem provers have this. But I want to do a real proof. And I am saying to do a real proof, I have my base case, I have my inductive case. Let me start by unit. And yes, Liquid Haskell says that both of these cases, it's like, I don't know, I don't believe you, because it's not enough information, right? So we have this, this was left. So we have this proof combinator library that comes from Liquid Haskell, and it just gives you like some operators that you can use to construct proofs. And in the base case, I'm going to do an equational proof. Like my x's is the empty list, I append it to the empty list, and this is equal to the empty list, QED. So QED, star star, and equal equal are parts of this proof combinator library. And like this proof is fine, right? I just did one step of unfolding, Liquid Haskell accepted it. So let's go to the inductive case. Again, I'm going to start by rewriting. X is append to the empty list, and then I say equal, equal, equal. I just push out X, and now I can use my inductive call, right identity on X's, and this is equal to X-axis, and that concludes the proof, and there is no more arrows. Like this is a good proof, and I think it's like really cool if you haven't seen that before, because you use Haskell to prove theorems, right? And so Liquid Haskell come with a termination checker. So if I say, like, if my inductive proof is bad, it says like this. It says like this error that basically says like there is nothing decreasing here. So this function is not terminating, which you can turn off if you want to actually write a terminating function. But if you use this to prove theorems, you need to know that your inductive hypothesis is good, which means you have to call it, you have to do the inductive call only on smaller things. And it also comes with like completeness. It checks that all your branches, all your cases are there. So yes, like this should be totality error, right? You haven't defined this function to all your possible inputs. If you see this function as a Haskell function, if you see this as a mathematical proof, it says that your proof is not complete. It doesn't cover all the input cases. Okay, so this is a proof, but it's kind of boring because I'm doing all the steps. So Liquid Haskell comes with a tactic that is called proof by logical evaluation, PLE. So I can turn it on. So this is Haskell comment. This is Liquid Haskell comment. So now I'm telling to Liquid Haskell activate PLE, which means that like you don't have to do the boring unfolding step. So this is something that PLE is going to do for you. So I return back to unit. This is something that PLE is going to, this unfolding PLE will do it for you. This unfolding PLD will do it for you. So I just need to have my inductive call. Okay, and this proof now is fine. Cool. Let's do one more. Now that we have PLE, associativity of list, I have 3 lists, x's, y's, and z's. And if I first append y's and z's, this is the same as if I first append x's and y's, right? And the proof goes by induction on x's. So I'm going to start like empty, empty, and then my inductive call. And it's fine. This is the proof of associativity of lists. I have my base case, PLE, complete the proof. I have my x's. I am doing an inductive call on the x's, and this goes through, right? Okay. Yeah, it's an easy proof. Okay. It's easy. It's, yeah, proof by induction and PLE. Okay, one more that is a little bit more difficult. Distributivity. Okay. 2 lists, x's and y's. I want to reverse x's and y's, and this is equal to reversing first y's, and then this is reverse x's. Okay. We hope, like generally, if you start a proof, you hope it's going to be like associativity style, proof by induction. Yes, and you hope that this is going to go through TVT x's y's, right? It doesn't go through this time because it needs more stuff. Okay, so, and this is a very common case, right? You start, you hope it's going to go through, it doesn't go through, and what you do, like remember what we did at the right identity. Oh, it knows it. Okay, I can, yes, like, I mean, I have done this, it's trained. So, let's see if it goes through, if it knows it well, right? Huh. Ah, okay, it doesn't know it. Okay, so if it doesn't go through, what you do is you start. Oh. Okay, so the base case needs right identity on reverse y's. And I don't know if you trust like Liquid Haskell and Copilot, or we could do the proof if you prefer. But what happens is you start from the left-hand side, right? Where x's is the empty list, and you want to eventually go equal to reverse y's, append reverse empty, and this completes the proof. Yeah, and we can like the cool thing is that this operator is basically checking that what you are combining. I don't have the Liquid Haskell. What your left hand side and your right hand side are equal. So I think like this is a very cool proof debugging thing. So yes, like if you didn't have this helper lemma, you're going to get an error in a good location. It says like, it says that I cannot prove that this is equal to this. So you want this helper lemma. So reverse empty list append y's. By the definition of reverse, we know that this is reverse y's. So right identity on reverse y's just puts just put reverse y's on the right hand side, and this completes the proof, right? Okay, and in the inductive call, let's see, like you need some, no. Okay, let's do it, no? Yes. Okay, let's do reverse x-axis and y's. This is equal, I am taking out the x, which is equal to reverse x's and reverse y's, and I take the append. This is by the definition of reverse, right? Which is equal to, now I have reverse y's. This is my inductive hypothesis, right? Cool. And now I am going to apply what we proved before. I'm going to apply associativity on reverse x's, reverse y's, and append. And this should be the end of the proof, no? Yes. Good. So I needed, like here, I needed this associativity operation. And as we said before, like this is very annoying because PLE can prove all the stuff as long as you give it the two big things, associativity and distributivity. So now that we have the full proof, we can make it unreadable by just removing all the things that PLE can prove. And yes, so PLE is especially in this kind of small proofs, PLE is working quite well. And we have an experimental other helper that is doing that is helping you with these proofs, and it's called like rewriting. And you can say like rewrite with, which means that put in scope associativity a right identity when you prove the distributivity. So now you don't need like you don't need to explicitly call associativity anymore. But this is like more, if you put it too many things, you are going to see it slowing down. Okay, this is the demo part. I'm going to go back to slides, but like if you want to play more, like we have an online interface of Liquid Haskell. You can download it from Hackads. You can download it from source, from GitHub if you want, and I am here the rest of the day if you want to play, if you want to prove something. Feel free to ask me. And yes, so let me go back to my slides to see like more or less what happened here and what are the possibilities of refinement types. Okay, so refinement types is this box. It takes as input a program and a property, and it has a set of rules, the refinement type inductive rules, that what they are doing is that they are generating a logical condition, and they are giving it to an SMT tool that automatically decides the validity of logical formulas. And they ask the SMT, does the program satisfy the property? If the SMT says yes, it means that it does. If the SMT says no, it doesn't, right? And so in our original example, the property was safe indexing. So basically, refinement types were generating a logical condition that was trying to prove that from whatever information you have in your background, you have to prove safe indexing. So in the first example that we knew nothing, basically the question was, can you prove safe indexing from true, from nothing? And the SMT said no. So Liquid Haskell said no. And then we changed the code so that we have like this path sensitive, like we have this condition explicit, and then the question was trivial. Can you prove like that if the condition is satisfied, it's safe indexing? So the SMT like trivially said yes. And then we saw like yes, so verification with refinement types is case sensitive, and essentially the whole verification reduces to put at the beginning of your program some runtime check so that the whole specifications go through. And another interesting feature that we saw, especially compared with other verifiers, is that verification with refinement types is type-based. And the example is that, the one that we saw at the beginning, that if you want to like describe that a collection, like a list, has some properties, you don't need to use any for all qualification. You just use the type structure and go and refine your types to the types that are contained to satisfy these properties. So verification is type-based, And this is very good because it allows us to, like this, to describe properties of containers, but remain in this SMT decidable logic. So we don't need to use for all, we don't need to use existentials. And these for all and existentials are very bad when you're dealing with SMT solver. So there is a term that's called the butterfly effect, and it says that if you give to the SMT like undecidable queries, you have the butterfly effect, which means that I am changing something at one point of my program, and verification like gets unpredictable, like undecidable in a different kind of your program. But with refinement types, we send to the SMT only questions from decidable theories. And how do you do like this more advanced verification? As we saw, like to do more advanced verification, we use these tactics, which essentially are layers that you put, but before you send the queries to the SMT solver. So we saw PLE, proof by logical evaluation, that is essentially doing function unfolding before you send the queries, and we saw these rewriting rules that, again, they are in semi-experimental, they work well, but in very small things. And all this processing happens before the SMT. Okay, so these are some of the features of refinement types: decidable, type-based, case-sensitive, SMT automated. And another very important feature is this, that they are language integrated. So as we saw, Liquid Haskell is part of GHC. It is a GHC plugin, which gives you a lot of flexibility. Like you have the Haskell language server, you have all the flight check integration. You can use it as a part of your CI cloud testing. And yes, you just like activate the flag to run Liquid Haskell on the background while your program builds. And these are very important, and these are some features of the refinement types that are there by design, and they make refinement types, like by design, they're designed to be practical. And in the rest of this time, I'm going to describe some other features of refinement types, which are if they are expressive, if they are general, and if they are sound. Okay, let's talk about expressiveness. And so as I mentioned, to keep this practicality of refinement types, it's very important to generate only queries that comes from SMT decidable theories. And these include like data types, linear arithmetic, like this greater than 0, different than 0. You have uninterpreted functions that are very important because you can use them, for example, to describe length. And yes, with these decidable theories, it's very direct to express things like safe indexing, like you can use it now, or like termination, totality are things that just work. And there are some other interesting features that like you can express, like sortedness or these recursive properties. You can use refinement types to refine recursive data type and express this kind of recursively defined properties. But you can use Liquid Haskell also to express domain-specific properties, what we saw as deep verification. And a domain-specific property that I have worked a lot is web security. And I'm going to give here an example. And as an example, I have program. The program manipulates data from a database. And so these data are protected with policies. For example, we have the secret data and the public data. And there is a very nice Haskell library by Dean Stefan that works with this policy separated of web application. It's called LIO. It is, I think it's a monotransformer, like labels on top of IO. It's a very cool library. If you don't know it, you can check it out. Okay, and this, so the goal is to show non-interference, that different labels, the secret and the public label, cannot interfere with each other. And that is that if I have a program that runs under the public privilege, it cannot depend on on secret data, right? And so building on top of LIO, we developed this information flow a security library that's called LWeb that basically uses runtime check to ensure non-interference when you're dealing with a database. And what we did is we used Liquid Haskell to prove that non-interference is actually satisfied. And the way we did this proof is that we proved that execution preserves what we call low view. And the idea is that if we erase all the protected data, the execution remains the same. So we need this notion of erasure. So I have a program, and I am erasing this program based on a label. This label is low, so I erase all the private red values from the database. And like the deep verification proof, the associativity or distributivity proofs, we prove the non-interference property that says that for each label L at two programs P1, P2, if I erase P1 and P2, then, and they are the same, they're low view equivalent, then the erasure of their result is also the same. And this is a very good example of using Liquid Haskell as a theorem prover, to prove interesting properties like non-interference. And this was the first biggest major proof in Liquid Haskell, 5.5K lines of code. And in this proof, I worked with a designer of LWeb, and we found 2 bugs, which was in these corner cases of checks. And yes, secure web applications is a domain that you can prove many properties because they are very well-defined properties, but also you can use refinement types and Liquid Haskell to prove other domain-specific properties, like resource usage with Graham. We have developed a monad that reasons about runtimes, or there is a proof about distributed applications. But the idea is this, that if you want to use refinement types for decidable properties in the style of safe indexing, out of the box, you can use them. You can use them now in your project, and it is also possible if you put a lot of effort to prove more sophisticated, deep domain-specific properties. And so, given that, I can say that refinement types can be quite expressive, if you want them to be. Okay, let's see about generality. I presented refinement types for Haskell. So the interesting thing is that refinement types actually started from ML, and porting from ML to Haskell, the tricky part was how do you deal about laziness, because interestingly, the original system, when we ported to Haskell, because of laziness, it was unsound, which means that you can have a false laying around. Yes. Okay, so Liquid Haskell is here, 10 years. It's still under development. But the interesting thing is that having this as inspiration, many more languages have refinement types. So last year, there is Flux, which is a refinement type checker for Rust. And there is an interesting work that develops liquid types for Java. Last year, there was this usability design query, but the project is still active. And there is, I think for me, the existing other main refinement type checker is Stainless, that has refinement types for Scala. And the idea is every year there are more systems that use refinement types. So the idea is that the principles of designing refinement types are general. And there is this tutorial that we wrote with Ranjit that tells you the basic principles of how to design refinement types for your own programming language. But then if you want to deal with specific features of the language, of course, you need to adjust and take care of how do you generate basically these logical queries to the SMT solver. But yes, the principles are quite general. And then we go to the last features, are refinement type sound. Okay, so let's see, what do we mean by soundness? So we say that a type system, like a refinement or unrefined type system, is sound when it only accepts programs that cannot get stuck, right? This is the standard definition of soundness for types. And it comes with a mathematical formulation that says that if an expression has a type t, and this type can be refined or non-refined, it's fine, and this expression E0 evaluates to an expression E, so then E is either a value or it takes one more step. And this means something that is typed, E0 that is typed, cannot get stuck. Either it keeps going or it stops with a value. Okay, so we ported this theorem to Liquid Haskell in the deep style of verification. And yes, so has type is actually it's a refined GADT that yes, we call it refined proposition. It's like Haskell inductive data types and models the refinement type checker. Again, evaluation models an evaluator. And we actually proved this theorem in 10K lines of code. And the proof is actually quite cool. If you have done any proof of soundness, it's like as if it was in the paper, but it's Haskell, like this is the soundness proof. And the proof k-splits on evals, so it k-splits on the evaluation. And it says if the value E0 is equal to E, which is a reflexivity, then apply progress. Otherwise, if you take a step, yes, call inductively soundness using the preservation. And it's quite cool because it is the standard preservation and progress soundness property expressed in Haskell. So yes, that is done. We proved it, and one could say that it's sound. But of course, that's not the full story, right? And it's not full story because we have Liquid Haskell, which is a real tool. And in Liquid Haskell, we have more or less 5 unsoundness reports per year, where an unsoundness report is an example program that is accepted by Liquid Haskell, but it violates the property. And this 5 is average, like stainless that I mentioned for Scala, also like F star, which also are refinement type checkers. Like I think they have the same number of unsoundness bugs per year. And I don't know if that's big or small, but like a good comparison is Coq or ROC. So ROC is a theorem prover, type theory-based theorem prover, and their designers say that they receive about 1 unsoundness report per year, right? So 5 is bad, but it's not terrible. So what is happening here? Why is this the case? It's the case because Haskell implements a core refinement type checker, which is the one that we have modeled and mechanized, and we know that it's fine. But it also has a lot of features that are not mechanized. So Liquid Haskell runs on top of GHE, so it accepts and analyzes all the core expressions of GHE, which has like these data types, including GADTs. It has some type inference. It has these coercions that like, I have no idea exactly what coercions are doing, but like Liquid Haskell analyzes them. Yes, so all these features were not mechanized in our proof, right? So Liquid Haskell implements this. We have a huge trusted code base that is doing the generation of the verification conditions, and we also trust GHC, we trust SMT. So there are many features that you can like use to find like an unsoundness bug. So the situation is quite different in Coq. Coq implements using a tiny like trusted code base, implements this CIC, calculus of inductive constructions, which is a theory that reduces to set theory. And we believe that set theory is consistent, right? And since there is this reduction, it means that CIC is also consistent. So this, like 1 per year unsoundness bug, is exposed because of this trusted code base that is very small. And actually the Coq people have started a project that they are trying to verify Coq in Coq itself. It's called the MetaCoq project, and it is a very interesting property, a project in this domain. So, in summary, we have like refinement types that, as I mentioned in the beginning, are designed to be practical, to exist on existing programming languages. And on the other side, we have a COC that is another dependent type verifiers that are designed to be sound. And yes, like this means that they implement an logic that is known to be consistent, while refinement type's goal is to be built on top of an existing programming language and add verification tools. And because of these different goals, like in refinement types, all the proofs are implicit, they come externally from solvers, while in dependent types, we have explicit proofs. And an example is that in refinement types, to prove that 42 has a refinement type, is just like the proof happens externally, while in COC you can use this syntax for refinement types, but you need to give like explicit proof terms. So like they have the same goals, the same expressiveness abilities, but their design is different. So here you need to be explicit, you are more sound. Here like you have like all this implicit external solver on top of programming language, but it is more practical. And ideally, what I would like to see is to like combine these two features, right? So you have the user that works on Haskell or maybe any other favorite programming language. You use refinement types and all these implicit proofs to verify your program, and then you generate, like there is a tool that generates proof certificates that are verified by a sound theorem prover. But until then, like again, like soundness is under construction, and I would like to thank you for your attention.
Thank you so much, Niki.
Thank you.
So, other questions? Yes, Christian.
So the soundness violations, they're only with regards to the Liquid Haskell properties, or also with regards to the Haskell type system without refinements? As in, is it a GHZ soundness bug, or is it...
No, I think like we didn't have any GHC soundness bug exposed, because the properties are expressed using the logic mostly. I mean, we had many bugs because we had some assumptions about how GHC functions work, and then maybe the interface changed and we didn't upgrade, so we had some bugs exposed, but it was not GHC bugs. It was assumptions that Liquid Haskell was making about GHC implementation.
Okay, but all the soundness bugs were basically GHC, or when you run the program, it throws an error at runtime, even though the Liquid
No, the
said it should not?
unsoundness is the other way.
Okay,
The Liquid Haskell is fine,
yes.
but the property is violated.
And how would that show itself that the property is violated by...
We will get a bug report by a user that says this.
Or the program doesn't do what it's supposed to, right?
Yes, you get the runtime error, or you've
No, you
proven
don't
something that,
Yes,
that
like
the proof
Liquid
is bad for the type.
Yes.
Okay.
So it's like in the first example, if I was indexing with I and I was and I didn't get this error,
Yeah.
it would be an unsoundness bug, because Liquid Haskell will say yes, but the property didn't hold.
Okay.
There was a counterexample. We don't care about completeness. Like if Liquid Haskell would say no at every program, it would be super sound.
Okay.
Next question.
Yeah, so in the very first example, before you introduced Liquid Haskell, you were comparing I to length of x's, which means that if x's is infinite, your program would then not terminate, and then you switch to Liquid Haskell. How would that handle an infinite list?
So a Liquid Haskell has a termination checker, which means that verification assumes that everything is finite.
Okay, so it would. So if you tried to pass an infinite list, Liquid Haskell would not accept it.
If you try to generate an infinite list, Liquid Haskell will not accept it.
Okay.
Apart if you turn off the termination checker. Because I mean there are techniques to reason about infinite lists, but they are not so easy. So if you want, we had a Haskell symposium paper that we were introducing some techniques to reason about streams, but they are you need to provide proofs. If you want just to have a simple bound checking, we assume that everything is finite.
Thanks.
Any other questions?
So you use the linear logic. I haven't read the Liquid Haskell way, but so when you work with like binary trees or even higher radix trees, does that turn into a problem? Because then like the number of elements becomes 2 to the power of x, or 3 or 4 or n to the power of x. And is that a problem when the number of elements is like a non-linear equation?
No, because we just use the specification. We don't do any symbolic things.
Okay. Yeah.
So yes, like when I see a tree, I care about the refinement type description of the tree. I don't generate, like Liquid Haskell is not generating any terms.
Okay.
Which is again it's imprecise, right? So if you have like a function, you just see its refinement type specification. You don't go inside the function, which means that we don't have these problems of verification being slow, but it is imprecise.
On one of the last slides, you talked about kind of the combination with a theorem prover like Coq. Is there also a possibility to have within the same language that you would use like dependently type programming for those properties which are not decidable, but you do have all the conveniences of SMT solvers and automatic checking for those properties which are decidable?
So you say let's combine dependent Haskell with Liquid Haskell.
Yes.
It is possible. Actually, right now, I think there are many. I have a student, and there are some people I think Gergo, they are trying to combine these things. Right now, what I mentioned, there are many crashing things because Liquid Haskell is not treating well the GDTs and coercions and all this, and now we are working on that. I don't know exactly what is the case study, but I see a lot of dependent types, a lot of GDTs being verified right now. So it is possible. I don't know what is a good what property goes where, but yeah, we are working on that.
Any other questions? Then, thank you again, Niki.
Thank you.